In the previous two videos, we understood how different earthing systems behave during an earth fault and how indirect contact can lead to electric shock. Now, let us move one step further and learn how people are protected against electric shock in a TT system, specifically, shock due to indirect contact. IEC 60364 specifies 5 measures for protection against indirect contact. Among these, automatic disconnection of supply is the most commonly used method. To understand how this method is applied, we must first recall a fundamental characteristic of the TT system. In a TT system, the power source, usually the transformer neutral, is earthed at the supply side through the system earth electrode. Inside the consumer's installation, the exposed conductive parts are connected to a separate protection earth electrode. These two earth electrodes are electrically independent. Depending on the installation, exposed conductive parts may be earthed individually, in groups, or together using a common protective conductor. However, regardless of how they are arranged, one condition is always present. When an earth fault occurs, the earth fault loop impedance is dominated by the resistance of the system earth electrode and the protection earth electrode. This impedance is relatively high. Therefore, the magnitude of the earth fault current is usually low. Because the fault current is low, normal overcurrent protective devices, such as fuses, MCBs, or standard circuit breakers, may not disconnect the earth fault within the time prescribed by the standard. That is why, in TT systems, residual current devices, or RCDs, are the primary means of protection against indirect contact. When an RCD is used for fault protection, 2 conditions must be satisfied. First, the disconnection time must be less than the time prescribed by the standard. Second, a voltage condition must be satisfied. Here, RA represents the total resistance of the protective earth electrode, and the protective conductor connected to the exposed conductive parts. And I delta N is the rated residual operating current of the RCD. In practice, the resistance of the protective conductor is usually very small, compared to the resistance of the earth electrode. So, for practical verification, RA is often approximated by the earth electrode resistance alone. This means that the product of the RCD's rated residual operating current and the protective earth electrode resistance must be less than or equal to the safety limit voltage of 50 volts. For special locations, such as temporary supplies, construction sites, and agricultural or horticultural premises, the safety limit voltage of 50 volts is replaced by 25 volts. Now, to apply the disconnection time requirement correctly, IEC distinguishes 2 types of circuits: distribution circuits and final circuits. This distinction matters because the permitted disconnection time depends on the circuit type. In a TT system, final circuits rated not exceeding 63 amps for socket outlets and 32 amps for fixed connected equipment must disconnect within the time specified in this table. For all other circuits, the maximum disconnection time is 1 second. This longer disconnection time allows selectivity between RCDs installed on distribution circuits. If all extraneous conductive parts of an installation are equipotential bonded, longer disconnecting times of 5 seconds, similar to a TN system, can also be used in a TT system. Now that the requirement is clear, let us apply this design rule to 2 electrical installations. In both cases, the nominal phase-to-earth voltage is 230 volts, and the resistance of the system earth electrode, Rn, is 10 ohms. The 2 installations differ only in the resistance of the protection earth electrode, Ra. In the first installation, Ra is 100 ohms. In the second installation, Ra is 15 ohms. Now imagine that an earth fault occurs in the final circuit. In the first installation, the earth fault loop current is about 2 amps. The contact voltage is the fault current multiplied by Ra. This results in a contact voltage of about 210 volts, which is clearly dangerous. Therefore, the affected part of the installation must be automatically disconnected. To satisfy condition 1, for a network with a nominal phase-to-earth voltage of 230 volts, IEC 6036 specifies a maximum disconnection time of 0.2 seconds. To satisfy condition 2, the maximum permissible RCD operating current is 0.5 amperes. This means an RCD with a sensitivity of 500 mA or 300 mA is required. For a 2 ampere earth fault current, an instantaneous 500 mA RCD will disconnect the circuit in less than 150 milliseconds. With higher sensitivity, the disconnection is even faster. An instantaneous 300 mA RCD will disconnect the circuit in less than 40 milliseconds. Therefore, in the first installation, either a 500 or a 300 mA RCD can be used. Now let us look at the second installation. Here, the earth fault loop current is about 9.2 amperes. The contact voltage is again the fault current multiplied by RA. This gives a contact voltage of approximately 138 volts. This level is also unsafe. Therefore, the faulted circuit must be automatically disconnected. Applying the same condition to the maximum permissible RCD operating current is 3.3 amperes. In this case, even a low sensitivity 3 ampere or 1 ampere RCD comfortably satisfies the requirement. An instantaneous 3 or 1 ampere RCD will ensure automatic disconnection of the faulted circuit within 0.2 seconds. But here is an important point, please remember this. The RCD sensitivity must be chosen for the worst-case value of the protection earth electrode resistance. Let us imagine that, in both installations, the worst-case resistance of the protection earth electrode is 200 ohms. In this case, the RCD sensitivity must be increased, that is, the rated residual current must be reduced to below 250 milliamperes. From this, we can see that the resistance RA of the earthing system directly affects the required RCD sensitivity. When RCD sensitivity is increased, meaning the rated residual current is reduced, a higher earth resistance is permitted. In other words, the earthing system becomes less demanding. For example, with a 300 mA RCD, the maximum permissible earth resistance is about 166 ohms. If a 100 mA RCD is used, the permissible earth resistance increases to about 500 ohms. You might be thinking, can we reduce the RCD threshold to any value? The answer is no. The choice of RCD sensitivity also depends on the total leakage currents in the installation under healthy operating conditions. To see why, we first need to look at the operating characteristic of an RCD. An RCD will not operate for a residual current less than half of I delta N. This is known as the residual non-operating current. The RCD may operate between half I delta N and I delta N. And it will definitely operate above I delta N. That is why, when selecting RCD sensitivity, it is necessary to consider not only coordination with the earthing system, but also the normal leakage currents present during healthy operation. In other words, if the total leakage current in healthy conditions approaches half of the RCD rated residual current, nuisance tripping may occur. To avoid this, the vectorial sum of leakage currents should not exceed 0.5 I delta N. Up to this point, we have seen that RCDs are well suited for protection against indirect contact in TT systems. This brings us to an important question. Can overcurrent devices alone be used for protection against indirect contact in a TT system? Well, IEC does allow this, but only under very restrictive conditions. A sufficiently low fault loop impedance must be permanently and reliably ensured. In TT systems, this is difficult to achieve in practice. Earth resistance values are often high and difficult to predict. As a result, earth fault currents remain low. To achieve fast disconnection under these conditions, very small rated overcurrent devices would be required. Often 6 ampere MCBs or even smaller. This is not practical for normal electrical loads. That is why, in TT systems, overcurrent devices are mainly used for overload and short-circuit protection, and not for protection against indirect contact. Therefore, overcurrent devices should be used for indirect contact protection only in exceptional cases, and only with great care. If overcurrent devices are used for fault protection, again two conditions must be satisfied. First, the supply must disconnect within the prescribed time. Second, the loop impedance condition must be met. This condition is expressed as ZS times IA should be less than U0. Here, ZS is the total fault loop impedance. IA is the current that causes the protective device to trip within the required time. U0 is the nominal voltage to earth. In a TT system, ZS includes the resistance of the phase conductor, the protective conductor, the protection earth electrode, and the system earth electrode. The overcurrent protective device must be carefully selected to ensure that both conditions are satisfied. Before we close, let us summarize. In TT systems, RCDs are the primary means of protection against indirect contact. RCD sensitivity depends on the resistance of the protection earth electrode. Higher sensitivity, that is, a lower rated residual current, allows higher earth resistance. Overcurrent devices have very limited application for indirect contact protection and should be used only in exceptional cases. Thanks for watching.